This is example number 2 on circulation. So we want to find the circulation of the following velocity field. Following velocity field, x, y, x plus y, x times y, j, along C. And obviously counterclockwise. And what we want to find it is across the following. We want to find this across this path. This is a triangle. This is 0. This is 3. This is 2. And what we're going to do is we're going to call this several surfaces. Okay, we're going to call this C1, C2. We're going to call this C3. Okay, remember it's a closed integral. That means that the total circulation will be equal to the line integral over 1 plus the line integral over 2 plus the line integral over 3. Okay, so in other words, what we are saying is the total integral of v ds will be the same as the integral over c1 of v dot ds. We're going to call this 1 plus integral 2 v dot ds2, this is segment 2, plus integral of ds3 over psi 3. Okay, so that's what we are trying to find in this problem. To do this, there's a very nice trick that we can use. We can use parametric equations because they will greatly simplify our problem. Parametric equations. So the way I like to do this problem is the following, and it's very easy to do this. So I'm going to do one segment at a time. Let's see segment number 1. So what you do is you say your segment R1, okay, that's going to actually equal to xy of segment x1, okay, and this is going to equal to following. This is a vector, I and j, by the way, okay? We're going to say this is the coordinates of this point are 0, 0. The coordinates of this point are 3, 0. The coordinates of this point are 0, 2. Okay, and this is going in this direction. That's what we know. And we're going to work now with segment number 1. Okay, so what we're going to do is you take the vector this minus this, 3 minus 0, and y2 minus y1, that's 0 minus 0. You're going to multiply that, let's say, a parametric equation, t. And you're going to add to that the initial coordinate system, that's 0, 0. Okay, so this becomes your new vector that defines this. And if you want to find this now, this is the new vector. And that means that your dr1, you can use parametric equation, chain rule that says drt dt. So you can take the derivative of all this. But before I do that, just give me a sec. It's convenient if I just go ahead and I add this up, vector notation. So this is 3t plus 0. I'm sorry, I don't need to put the 0 there. And this is 0. Okay, so this is what this vector becomes. So what I'm saying here is now take the derivative of t of this vector, 3t, 0, it will be dt. And then you just take the derivative of each one of these components. The first component, derivative of t respect to 3t will be 3, 0 is 0, this is dt. Okay, so this represents your first vector. Now, also note that f, the flow across this line, I have to, the flow across this line, the velocity was given by x plus y plus xyj. So the velocity, let's say in this segment 1, across this segment 1, x is going to equal to, you see, x is equal to 3t, 3t plus y is equal to 0, I, plus 3t multiplied by 0, this is j. So this is actually going to equal to 3ti. So this is the vector. And if you do the parameterization like this, you just have to integrate 0 to 1. That's the beauty of parameterization. So this integral will actually be 0 to 1. Okay? So let's complete that integral. We will do that integral later. So now let's go and do the parametric for segment number 2, and give me a minute. This is segment number 2, and then segment number 2 will be the same thing, right? I said 0 minus 3, 0 minus 3, y at 2 minus 0, this is multiplied by t, plus my initial coordinate. But remember, I'm going in this direction, so this is my initial coordinates. This is 3, 0. So I can do exactly the same thing. I can say my dr2 is going to be partial of r2 respect to t dt. So if I take the derivative of this respect to time, I can write this completely. This is minus 3t plus 3, because I multiply this t by each one of these components, 2t, okay? So now I take the derivative of this, minus 3t plus 3, 2t dt. So that will give me minus 3, 2 dt, okay? So your velocity vector, let's say 2, that was equal to x plus y I, x, y, j, that would be equal to minus 3t plus 3 plus 2t I plus minus 3t plus 3 times 2t is equal to j. Okay, and you also integrate this from 0 to 1. Let's do segment. This is segment number 2. This is the one that we are doing now. Okay, this segment. Now let's do segment number 3. So we're going to do segment number 3. This is this segment. Note that the arrow is going like this. I'm always going counterclockwise. I'm going in this direction. So this is segment number 3, R3, and I'm going to do the same thing. Okay, so I go from x2 1 minus x2 minus x1, but I'm going this direction, so 0 minus 0. That's 0 minus 0. This will be 0 minus 2, 0 minus 2 times t plus My initial point is this one because your vector is going this direction. So it's 0, 2. And this gives you 0 minus 2 plus 2. Okay. And then if I want dr, that would be partial of r3 respect to t dt. That's partial of t, and that gives you 0 minus 2 minus t plus 2 dt, and take the derivative of the first term, this is 0. Derivative respect to t, this is minus 2 dt. Okay, and then also velocity field acting along this segment would be x plus y j plus xy I plus xyj, and x is actually 0, y is minus 2 plus minus 2t plus 2 I plus this is 0 times minus 2 plus 2j. Okay, these are the easy way to do the problems. It's very straightforward. Okay, so now what we're going to do is, now you say your total circulation is the integral. Since we already did parametric equations, I just integrate 0 to 1. That's the beauty of it. Okay, so this is velocity 1, velocity 1, dr1 plus 0 to 1, velocity 2, dr2 plus velocity or 0 to 1, velocity 3 dot dr3. Okay, so if I did this, this will actually give me, this will be equal to the following. So the first segment, I found my velocity is 3t. So this is 0 to 1, 3t, I dot this is 3t 3i 0 dt. Okay, so this is what the first segment is, and this gives you a value of 90. Okay, then this is plus 0 to 1. This is the longest term that I have to take. Is all this term and all this term, and that gives you a value of so that gives you, this is this term, this is this term right here. This there's 3 and 3 there. This is what x and x is. So I multiply this times 266. That's why it's a minus, and there's a 60t squared. And then your r dr is minus 3 plus 2, minus 3 plus 2. Okay, so your last integral would be 0 to 1, and v3. This one is also easy. v3 is actually, this goes to 0, so you're just left with this term. So left with minus 2t plus 2 I dot dr, that gives me minus 2 j d of x. So this is actually equal to 0. And so what this is basically saying is the circulation along the third path is 0 for this velocity field. So This gives you 9/2. The integral of this gives you 9/2. This integral gives you minus 11/2. This gives you, the integral of all this gives you 0. So that means your total circulation is actually equal to minus, is equal to plus 9/2 plus minus 11/2 plus 0, and that would give you a value of minus 2/2. That gives you minus 1. That is the value of the circulation. And the units of this, if I was going to place some units, this would be meters squared over s. It could be, so circulation can have either that, or it can be inches squared over s, can be feet over s. So it's whatever it is L squared over s. So that is the total value. So the circulation is negative. So because it's negative, it's actually saying that your circulation is going in this direction and is equal to 1 in this direction, and it has a value of 1. Okay, so this is a good way to always write down your answers. Don't just write numbers with plus minus signs. Just make sure that people know what that really means in what direction it's saying. So what he's saying is, for this particular velocity field, the circulation occurring here happens in this direction at a rate of minus 1. That is the total circulation in this enclosed area for that velocity field.